Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number... Energy forecasting has been an obvious industry use case for time series. Energy can't easily be stored for later. It needs to be produced on demand, or pretty close to it. And to do that, the operators of these systems need to make forecasts, and that requires software. In this episode, I interview Erin Boyle from Myst AI about a platform they're building to help bring the tools of machine learning to real-world use cases in this sector.
My name is Erin Boyle, and I am the head of data science at Myst AI.
Could you give us the high level on what Myst AI does?
So Myst AI offers a time series forecasting platform and service with the objective of positively impacting sustainability. So for the coming years, we're laser focused on serving specifically the renewable energy transition by empowering data scientists and organizations in clean power broadly to quickly and easily deploy more accurate, reliable, and scalable forecasts.
Well, you've got a background in data science. Could you talk about some of the skills that were specifically called for in your role at Myst?
I've spent the last 6 years in the broader Silicon Valley tech sector doing machine learning. So I've been at Myst a little over a year. And prior to that, I actually worked at Stitch Fix for 5 years, where I was building large-scale real-time recommender systems. So absolutely, machine learning is a core component of Myst's skill set. And actually, it's something that's really valuable to the climate tech sector overall. So machine learning is absolutely one skill set that's super valuable, as is honestly just software engineering you see everywhere in climate tech. I think something that's really unique about Myst is that we're not built by only data scientists and engineers out of Silicon Valley. Our co-founder, Tishan Palazzi, came out of the Rocky Mountain Institute, and other folks on our business team also have a strong background in clean power. And I actually think that's super critical. And the people that kind of bridge this space are some of the most important, because at the end of the day, the types of problems that folks are trying to solve that are related to climate change really also involve understanding the real world. They involve understanding how power markets are regulated and how companies in clean energy make money. And all of these things come into how you can best provide value to these customers, if not into the actual modeling itself. And so I would highly encourage anyone who's interested in working in the sector to really build up skills on both sides, to work on technology, but to also really try to understand a specific industry they're interested in, and to reach out and to try and meet people in that particular industry that understand what makes it tick.
What does the energy sector need a forecast for? What's the decision they want to make?
Yeah, so there's actually a lot of answers to this question. So maybe I can give you kind of a bird's eye view here. So forecasting is a critical component of the clean energy transition for a number of reasons. To set the stage a bit, our electric grid needs to undergo a sea change right now for basically two big reasons. The first is that its power mix is moving from power sources with controllable supply like fossil fuels and nuclear power to power sources with more intermittent and harder to predict supply, like renewables such as solar and wind power. And second, because of climate change, we also have things like more extreme storms and fires and heat waves, which cause both supply and demand to be more difficult to predict. So one big reason that accurate forecasting is essential is to bring supply and demand into balance, which is something that the electric grid requires. These need to actually be balanced in real time. It's kind of an amazingly complex problem that is being solved today. But then accurate forecasting is also needed by all the individual players in the power market. So if you want to read about this a little bit more, you could actually go to a blog post written by our co-founder, Tishan Palazzi, who came out of Rocky Mountain Institute. It's at blog.myst.ai. He digs into some examples of this, but broadly, there's a few big examples. So renewable asset owners, renewable power providers, need to optimize those renewables. So essentially, because market prices of electricity can vary wildly, selling renewable production or other services into the most optimal market can greatly influence the value of a renewable asset. So in order to unlock the kind of growth in solar and wind that's needed to be on track for net zero energy related emissions by 2050, it's really important that these assets are profitable and are compelling for investors so we can really build out more solar and wind. So price forecasting is a critical component that many players in the market need. Other examples are similarly to dispatch battery storage. So right now, storage is a fairly small component of the grid. Supply and demand are balanced in real time with very little benefit from storage right now, which is kind of amazing. But storage will play an increasing role in the grid in the coming years to help balance some of the intermittency from renewables.
Maybe just to give you a scale for the rate at which storage on the grid is growing, it's really pretty remarkable. So this is a kind of late breaking update, but in California, we are set to finish the year 2021 with about 2,500 megawatts of battery storage installed on the ISO's grid. This is up 10x from about 250 megawatts in the summer of 2020. This is a really significant penetration. So if you take as reference peak load in California, this represents about 5% of that instantaneous peak load. So this kind of growth is happening all over the country and the world and is one big reason to support this industry with forecasts.
So you're building a platform for a specific industry. Can you talk a little bit about the motivations and design principles and ideas that went into that?
So to give a little bit of background on how we got to this point, Myst has spent the last 3 years partnering with organizations in this sector to solve their unique forecasting problems through our forecasting service, in which Myst's internal team both develops and serves forecasting solution to contracted customers. And we're super proud to serve almost a dozen really awesome companies, including 3 of the world's 10 largest power companies. And at this point, we're now taking everything we've learned in that time and are building it into our platform for more scalable impact, where organizations will work with us in one of 2 paradigms continually through our forecasting service that will go on, and also through the Myst platform, which is a tool for data scientist customers to build and deploy forecasts autonomously.
So can you get into how your customers derive value from the platform?
The value that they derive, we like to think of this as enabling them to really easily build models that are accurate, reliable, and scalable. And as the head of data science, of course, I'm particularly focused on that accuracy point. We really, at the end of the day, want to make sure that our customers are getting really accurate forecasts that are increasing the value of their own companies. So we like to think about that accuracy impact in 3 broad categories. And I think this kind of differentiates us from like some of the other ML platforms out there, even beyond our time series focus. So the first category is machine learning. That one's obvious. So the way we approach this is we provide an interface to the best ML-based forecasting approaches. So this can be state-of-the-art models, optimization methods, rigorous experimentation. The focus here is really on access to the best existing technologies. So our data science team ensures that we've selected all the best technologies and built them into our platform for easy use for our customers. The second pillar of accuracy is data. And probably I should have started there because at the end of the day, data is everything. So Myst's approach here is to build up a vast feature store of time series data that is pertinent to our customers' problems. So the data science team here explores a number of third-party vendors and assesses the various data sources that they have to ensure that those sources are surfaced to our customers. And then the third is by an AutoML engine that bridges these 2. So we have a bunch of modeling approaches. We have a bunch of data. Each of these are going to grow over time. How do you best and most efficiently leverage those 2 components? And the answer to that is by an AutoML engine. So that engine, should customers choose to use it, they can also choose to go a more manual route, will effectively search across a large catalog of models and time series to find the most optimal model and feature configuration for any forecasting objective.
Do you have a sense of, or is there a benchmark we can look to for how big the opportunity is? Or even maybe how different power grids or farms or producers in the energy space can take advantage of this? Are you an incremental or a game changer, or where do you fall on that spectrum?
Yeah, I mean, it's a great question. I think that a forecasting platform is a game changer because right now, what we basically see in the industry is that all of these different organizations are kind of reinventing the wheel because there isn't a great centralized solution to this problem. And the electric grid is changing so rapidly that the scale on which people need better forecasts is extremely large. Our customers are building out new projects at a rate that is hard for them to keep up with if they're kind of treating each new problem as its own data science project where they have to go find all of the data and build their own solution. So we think a centralized repository of both the data and the modeling solutions will unlock significant growth and efficiency in this sector.
As far as opportunity, I know I mentioned earlier the remarkable growth of storage and renewables. I think one kind of dollar value benchmark to give people some understanding of this is that one customer of ours, Enel, they are the world's largest electricity company by some metrics, and we currently help them forecast intraday market imbalance in Italy. Enel expects to invest 70 billion euros in this decade into new renewables, and that will result in adding about 84 gigawatts of new solar, wind, and storage capacity. 84 gigawatts, bring it back to our reference before, that's about 2 peak load Californias. This is from just one company. So again, I'm trying to draw a picture of the scale on which the grid is changing all over the world, and therefore the importance of helping this industry kind of be efficient and grow as quickly as possible to get a handle on the changes that can help us mitigate climate change.
So when you're going to engage with a new customer, they've got a bunch of data that they maybe haven't done anything with yet. You're going to help them do something actionable. What are the steps to get there?
So to describe what that looks like, it depends a little bit on the specific problem that a customer is trying to solve. So, I mean, one major kind of fork is whether they are solving a problem that relies on their own data source or on some kind of public data source. So for public data sources, for example, wholesale electricity prices, we actually don't need data from the customer, and R&D around how to properly forecast electricity prices is something that's kind of ongoing at our company and that we can provide solutions to upon request from specific customers. But then for organizations that are forecasting some kind of internal data source, so our load serving entity customers would be a great example of this. For example, we've worked with 3 different CCAs or community choice aggregators in the Bay Area. And in their case, we are given access to their historical load data for their service territory. And what we've done is we have built out end-to-end AutoML solutions to the load forecasting problem. So over the years, what this has meant is identifying all the most critical sources of data to use as features for these models. Of course, at the end of the day, features is king, so I'll start there. Electricity demand or load is highly dependent on weather. So we've put a lot of time into making sure that we have the kind of most accurate weather data and that the way we handle it is very thoughtful. So kind of interesting detail in the forecasting in electricity space is that you're often building forecasts on top of forecasts. And there's a lot of really interesting challenges that come up with that. You might, for example, for weather, you might only have historical, what we call actuals of weather, what weather actually occurred. You don't always have access to historical forecasts. But then, of course, at the time you're making a prediction, the forecast for the next day or the next week is really important.
So you've got the client data. Can you speak a little bit to some of the algorithms and techniques you use?
This is something that I won't go into a significant amount of detail on because we do keep our forecasting solutions somewhat proprietary. But I think that for both our forecasting service and soon our forecasting platform, you will find, as far as models, you will find many of the kind of conventional winners that you might see in things like the M5 forecasting competition. So we have experimented deeply with things like gradient boosted decision trees with different network architectures. You're going to see things like RNNs and LSTMs, multi-layer perceptrons. And actually, something that we really pride ourselves on is making ensembling in our platform a first-class citizen. So something that you'll see a lot in the literature is that ensembled approaches, and here I don't mean just like an ensemble like you might see in gradient-boosted decision trees, but ensembling on top of different modeling approaches. You'll often see those performing really well for real-world problems, and I think this is probably related to the data constraints that are inherent to modeling in sectors like the electricity sector. So the Myst platform has a unique framework that makes it really a first-class citizen to build out ensemble solutions. So this can be both kind of simple things like ensemble averaging, but also more interesting graph architectures. So for example, you can see things like stacking different models, having the forecasted output of one model be an input to another. We've done things like draw from a mixture of experts in enabling our users to build solutions that leverage different models at different forecast horizons, or different models, or even models that contain different data, because you might have different data availability or different data quality at different horizons of your forecast if you're forecasting out, say, a week. So these are all the kind of modeling approaches we've explored. I mentioned data. We pull in data that is related to weather. We have a significant catalog of data around power markets themselves that we use for much of our modeling. And then we have leveraged Bayesian optimization for things like hyperparameter tuning and feature selection, and have wrapped it all together with end-to-end AutoML approaches that are designed for a specific domain. So, for example, load forecasting or price forecasting.
Oh, that is a pretty novel data science-y kind of challenge there. You have the real, but not what the prediction was at the time. Do you then have to adjust, or how does it play out numerically?
So I think there are actually a few levels of complexity to consider here. And I might actually start with those that are more on the engineering and user experience side instead of the data science side. So the first is just kind of the most basic engineering challenge. You might imagine that the simplest thing a data scientist could do in this circumstance is to model these actuals and forecasts as all one time series. This works reasonably well in many use cases, and it avoids some complexity. However, it turns out that for the weather providers that we use, historical actuals are just literally in a different API than forecasts. So they need different data manipulation. And one thing that our data model makes very easy to do because of the prevalence of this kind of forecast and actuals concept is something we call layering, where the user can really easily layer one forecast on top of its actuals and kind of stitch the two together in a seamless way. It's a simple concept, but it just makes it easier for a user to start from the most obvious thing you can do. Then kind of moving in order of increasing complexity and returning to your question about how this might impact the data science workflow itself, I'll also just start from the simplest thing a data scientist might do to address this. So the first thing you might check is just how will this impact your results in production? How can you update your backtests and also your model tuning and feature selection processes to be reflective of what this behavior would be in production? So to describe that, let me just first review quickly the backtesting methodology we use at Myst. We use the cross-validation method that is sometimes called rolling origin cross-validation or walk-forward cross-validation. And the idea here is that you create a large number of folds where that origin, or you might call it as of time, is stepped forward chronologically. And in each fold, training only occurs on the data preceding that as of time, and predictions are made for some window subsequent to that as of time. Something really cool that you can do with Myst data model and our storage of historical data is run a backtest that is what we call as of time aware. So just to quickly give you a definition, in our data model, we store all time series with two time axes. One is natural time, which is kind of the regular time axis that you might think about. It's when events occur. And the other is as of time, pretty common concept in the ML world, but this is the point in time from which you reason about events happening. So maybe a job runs and makes a prediction. So we store all of those time series with those two time axes. And when we make our backtests as of time aware, this means that each of those fitting and predicting jobs under the hood in that rolling origin cross-validation are able to optionally use that as of time to only pull in the data that your model could have been aware of at that point in time in the past. So this could at least allow a user to know, like, how would my model truly perform under the situation of using forecasts at prediction time? And can I actually tune my model to account for that in some ways by maybe changing something about the features or the hyperparameters or the model itself? I think the subsequent levels of complexity get a little too in the weeds for a podcast. These won't be in our initial platform launch, but they would be to do things like train on forecasts instead of actuals, or when available, bring into consideration things like the prediction interval around the forecast input feature. There are some interesting paths forward here, but I'll kind of leave it as an exercise to the user to think about what might be involved there.
Thanks to today's sponsor, Nomad Data. If you've been listening since 2016 or went back through the archives, you might have encountered our Potholes episode. It was my experience interacting with the Los Angeles City data portal. It was a bit of an adventure, really, and had to get help from someone from the city. Shout out to Chelsea if you're still listening. And I've always been a supporter of these data portals. I think they're important, but navigating them can be a little rough. More recently, there's been this advent of data marketplaces. You've got Amazon, Azure, and Snowflake doing their own thing. Big players with no parity across them. It's not the data ocean we were promised, it's the data temple of doom, and I don't have time to be Indiana Jones. That's why I was excited to learn about Nomad Data. They're more like a matchmaking service. They're connected with some of the biggest data resellers in the world. Their technology takes your request and matches you to the ideal potential data providers. Here's one of the examples over at nomad-data.com. I'm looking at investing in European telecom markets, and I need detailed information about what broadband service each carrier offers, and actually gets a bit more specific from there. I don't know where I would begin to gather a data set like that, except to go to Nomad Data and put in my own request. If you need to make business decisions now, you don't have time for a research project about data. Connect with the right provider and start moving today. That's what Nomad Data can help you do. So head over to nomad-data.com and tell them what you're looking for. Thanks to our annual sponsor, Weights and Biases, the developer-first ML platform. Weights and Biases is an enterprise-grade platform that gives you experiment tracking, dataset versioning, and model management. Their solution integrates with TensorFlow, sklearn, XGBoost, Hugging Face, and literally every other framework I could think of. Integrating with your model training process takes just a few lines of code, and there's even a nice live notebook on their site that'll show you how to get it going. Once your machine learning code base or notebook is wired up, you've just unlocked the next level of productivity. The Weights and Biases platform collects, aggregates, and beautifully displays all of your key metrics and telemetry so you can track your model training in real time and compare different runs. Have you ever had to screenshot a matplotlib graph that you drop in an email or in Slack to show your boss the results of your work? That's like serving a gourmet dinner in a cardboard box. With Weights and Biases, all of your collaborators can see the results of different runs with an idealized interactive suite of tools. You no longer have to be the single source of truth for your whole organization about how the model's doing. If you're on or leading a growing team of machine learning practitioners, you need to investigate if Weights and Biases is the right solution for you. Get started at w&b.me/dataskeptic and mention us when you request a demo. Well, there must be some inherent unpredictability in this, like just the fact that the weather's involved, and that could be a decision whether or not a sign is turned on or off that consumes a lot of power. You can't make perfect predictions. How close can you get?
It's actually just so dependent on the problem. So obviously I can't really give you exact metrics, but maybe to give you a bit of a flavor, we know from our service customers that we're highly industry competitive. So that's one good starting point. In terms of percent errors, so for mean absolute percent error is a very popular metric. It's not the right metric for every problem, but let's use that one for now. In something like electricity demand forecasting, you might see low single digits of mean absolute percent errors. And again, this is so dependent on, what region you're forecasting in and, how exactly these customers settle. Do they settle on meters? Do they settle on profiles? But you can get very low single digits of mean absolute percent error in easier cases, and then it would be a little bit higher than that in harder cases. A target like real-time electricity prices is kind of an inherently noisier and spikier target. And so actually that's a good example of MAPE not being necessarily an ideal metric. The distribution can be pretty skewed, but that's the kind of problem that's a lot harder because it's subject to the whims of a lot of market forces.
Just to ballpark it, that around the holidays there's going to be more electric consumption for Christmas lights. Is it to the refinement where we can look at a few decimal places, or are these really things that need to be constantly updated because it's such a dynamic system?
Oh, constant updating is definitely part of this. So we certainly follow all best practices as far as continual retraining of our models. And we really seek to develop models that are highly adaptive and reactive to changing circumstances, which is just critical in this world because the electric grid itself is just changing a lot over time. The power mix is changing, demand response is changing all the time. More people are putting in solar and storage. Things like COVID really change things like demand and supply of electricity. So absolutely, you will see that the models, they're going to be more difficult on days that are outliers. And so outliers include things like heat waves, holidays, whenever there's been any kind of like step function in human behavior, like whenever on lockdown for COVID, certainly we saw our behavior change. But actually, I mean, our models really are quite adaptive. So actually, even though you can really see the significant change in use of electricity that happened during COVID, that actually didn't really impact our accuracy. We really maintained quite good metrics throughout that time. It's actually pretty hard to see any like step function in our metrics due to COVID. So I think that kind of speaks to the importance of having machine learning based models supporting this entire ecosystem and models that are using all the kind of ML ops best practices in order to make sure that forecasts remain highly accurate under changing conditions.
When describing the way you can ensemble not just the ML ensembling, but also ensembling approaches, if we look through all the approaches, would these be things that a seasoned data scientist would know, or are there any industry-specific type models that you have to apply as well?
I mean, there are certainly models that you see being used in the industry that in forecasting that maybe aren't used elsewhere. So folks have drawn certainly from natural language processing in forecasting. So you see things like RNNs being really popular in forecasting, like they were in NLP kind of a few years back before the rise of the transformer. And you see them being adapted to forecasting. So, for example, Deep AR has kind of adapted off of an LSTM in order to provide forecasted prediction intervals. This is something we also see plenty of our customers being interested in, is being able to forecast not just a point estimate, but a prediction interval for where your observations may fall around that point estimate. And so, yeah, you might look to specific methods like Deep AR for that. You might pull from other methods. You might use quantile regression, say. There's also, of course, statistical methods. So plenty of people will still use popular methods like ARIMA. And then this platform will certainly allow our users to access those kind of benchmark models as well. But we certainly see that machine learning models perform better.
With regard to the platform, is it a no-code solution, or how does it fit into the latest buzzwords of design for environments like that?
Essentially, what this platform is a platform that offers users the ability to build and deploy end-to-end machine learning-based forecasting workflows. So this means we're managing all of the infrastructure, but allowing data scientists to focus on designing and experimenting with solutions to their particular forecasting problem. It is only no code if you want it to be. We do provide ways for folks to build forecasting workflows solely through our web UI, but we anticipate that the vast majority of our users will be using our Python client library because we are focused on ensuring users have the kind of granular control over the way they want to build and optimize their particular solution that programmatic interface offers. So what that looks like is we offer this time series focused framework that enables users to create a DAG or a graph that's composed of time series data sources and transformations on those time series that leverage common open source modeling and data analysis libraries. So on the data sources side, customers can both access our data store of third-party data. So this is the features I mentioned earlier, like all sorts of weather features, power market features, and so on. Also just kind of all the typical like time-based features that one might expect in a forecasting solution. And then the transformations will be built off of, typical modeling and data analysis libraries. So things like, pandas and sklearn and PyTorch and XGBoost and things like that. So users will be able to, if they wish to, really fully tailor the solution that they're building and deploy it onto our servers. We will additionally provide ways for users who maybe don't want to build every transformation of their model to use more automated AutoML approaches. The platform additionally supports experimentation, deployment, scheduling, and monitoring. Like I mentioned, the user interface for many of those will be a Python client library. Users will probably use this for things like graph development, for scheduling, which we make extremely easy. Like it's really one line of code to schedule the cadence on which your model retrains or the cadence on which it makes predictions. Similarly, experimentation will be very easy to do through our Python client library, and then also querying forecasts. So querying your final output forecast, but also auditability is something that we care a lot about. And so our users will always be able to access all of the intermediate time series in their forecasting workflow for a current run or for any of their past runs. All of that data is stored on our servers. And then the web UI, we expect users to be using that for visualizing. So you can go visualize any of the graphs that you've developed. For monitoring, so you can see the jobs that have been running. And then for experiment tracking. So, we're excited for users to actually use our platform to try a bunch of different models, a bunch of different features, things like, hyperparameter optimization. We'll offer all of that, and they'll be able to track their results and to, promote new versions to be deployed in our web UI.
So for a listener who's comfortable in a Jupyter notebook, knows pandas and sklearn and some of the libraries you mentioned, and they want to get onboarded, what are the steps? Do I pip install and go from there? What's the coding experience like?
That's exactly right. And with one little asterisk, which is that for right now, we are behind a sign-up wall. So I think I mentioned that we'll be launching the Myst platform in early 2022, but initially behind a sign-up wall. And this is because our focus up until now has been more on the enterprise customers. And we want to make sure that we are giving them our full focus. And we are kind of transitioning from solely serving them via kind of a solutions consulting partnership to now serving them by enabling their data scientists to build their own solutions. But we have as our highest priority that we are very focused on those customers in the short term. So once you have signed up with Myst, you'll be able to pip install our client library. We actually have a really nice little tutorial for this. It's pretty amazing. It's really only about, 25 or 30 lines of code to pull in a ton of really valuable third-party data sources, which, we've kind of done all the difficult kind of like data formatting and wrangling of those third-party sources for the customer. Just, one line of code to pull in each of those, a line of code for each kind of pandas-esque transformation or model that you want to run, a line each for, the cadence on which you want your model to fit and predict. And then you simply have to deploy it. And after that, everything happens on our end.
So in my mind, I'm drawing some parallels to PySpark, where I might write some PySpark code, and when I execute it, depending on how I've it configured, it's actually going to go to a distributed cluster, get processed there, and come back to me. So I get this sort of single-threaded kind of experience of distributed computing. Is your system similar? Are you running the models, or are they local and you're managing them? Where does all the compute take place?
The compute takes place on our servers. And yes, our goal is for this to be distributed and scalable. So, these are actually hitting APIs, and we'll be able to parallelize larger computations on our end.
And is there a scope or a horizon you're chasing that's hard? Is the volume or the velocity of the data? What's really the cutting edge of what you need to work on from an engineering perspective?
To start with, our existing approach, which is allowing these fully composable forecasting workflows that aren't constrained to just a couple models, but rather flexibly support a broad suite of models and feature transformations. That means creating this time series focused data model and kind of increasingly adding more and more functionality around it. So I think I might have mentioned earlier that our approach to this is to create a framework where all the nodes in the graph pass time series between them. I described earlier some of the interesting challenges around folding as of time from our data model into more and more advanced experimentation features. So that will definitely be challenging and fun. I described earlier some of the interesting implications for both leveraging forecast inputs to models, but there are also implications for better treatment of historical endogenous data. What we've seen is that in certain domains that we serve, in particular electricity demand forecasting, historical endogenous data changes over time. So essentially, it's really hard to know exactly what happened on the grid quickly, and it actually takes up to 2 months for what's called the final settlement data to come in many cases. And there's actually interesting ways that you should fold that into your model development as well. And so that's another example of kind of expanding the functionality of our experimentation. Beyond that, so longer term, obviously, we're going to continue adding new third-party data providers. Some of our third-party data providers have like really interesting and complex data storage on their end too. So sometimes they have as of time in their databases, and we'll be able to increasingly surface that to our users so that they can query upstream data in more complex ways. Also, on the engineering side, we want to give data scientists users more and more flexibility as time goes on. So right now, in our initial platform launch, local development won't be an option, but that's something that we have on the roadmap. Additionally, we've been thinking about how we might enable users to provide custom model connectors at some point in the future so that they can even go beyond just kind of, I shouldn't say just, but go beyond creating these like composable pipelines from all of the components that we offer, which are already like a really impressive suite of components, but some more advanced data scientists really want like highly granular control over the model itself. And so in the long term, we would like to enable more custom code to also run in our workflows. And beyond that, I think, many of the typical scaling challenges of platforms and responding to all of our users' needs.
Well, from what I know about the platform, it sounds like a lot of these efforts make the techniques much more accessible and easier, whereas previously you'd probably need a senior data scientist to stand this up. Someone who doesn't have all those qualifications or has different qualifications could be the operator of Myst. Do you have a sense of who the typical user is going to be?
Yeah, it's a great question. I think we really hope to be able to serve a variety of users because we really want to empower the industry broadly. And we do think there are a variety of users in the industry. So in our forecasting service, we're empowering customers that may in some cases have fairly limited or maybe not even any data science team, but they need forecasts. In some cases, we may also have more, sophisticated data scientists that are excited to be able to leverage a platform where the data is like already formatted and ready to go. They don't need to waste their time on the kind of data munging aspect. Perhaps they don't need to, involve their engineering team anymore because we manage all of the infrastructure. So the deployment, reliability, security, all of that kind of stuff. And so they can still focus on doing interesting experiments. They will be experimenting with the data, with transformations, with different models, with different parameterizations of models. They can experiment with different optimization approaches we offer and with different ensembling approaches. So they really still have quite a bit of actual science that they can do, but they can do it without worrying so much about all the kind of surrounding engineering overhead.
How concerned are your customers with model interpretability?
I think, again, this depends a lot on who the customer is. And so I think for plenty of people for whom accuracy and reliability are just the really principal concerns, where we see interpretability coming up is usually where customers want to anticipate what's going to happen in a specific type of situation. So, for example, something we hear requests for sometimes are understanding the scenario of what is going to happen to my demand forecast if the temperature is 2 degrees higher tomorrow than we think it's going to be, or than like the point estimate forecast is. So there's obviously a few ways you can get at that question that aren't interpretability. So one thing is you can do something like forecast a prediction interval. Another thing that it will be possible for our users to do on our platform is to just literally generate that scenario. So to create a forecast where they manually add 2 degrees to the temperature and see how that impacts their forecast. Like they will be able to assess specific scenarios like that. On the interpretability side, obviously, if you're doing model development, this can be of interest to you. So for example, you might look at SHAP values in order to understand how important a certain feature is to your model, what kind of impact it has on the final forecast. That is the kind of thing that we hope to build into our platform over time to enable better development as well. Users will also be able to download other artifacts of their runs. So, for example, you will be able to download the fit state for any fit that has occurred for your forecasting workflow. So you will be able to actually query that actual fit state, query the inputs to it, query the forecast. You'll have all the ingredients you need if you want to do any kind of analysis in a Jupyter notebook locally yourself. Outside of our platform, there's nothing that will be hidden from the user that would prevent them from doing any of the kind of typical analysis they would pursue.
Well, aside from the obvious answers of growth and adoption, I'm curious if you can hint at what's next for the platform. Is there any lines of research or algorithms that you're interested to add, maybe external data sources? Where are things going?
I think for right now, our focus is on getting it launched. I would say everything you just named is absolutely an ingredient of that. And so third-party data sources, models, we are excited and feel good about the suite of models and data sources that we've decided upon for launch. And our primary concern right now is getting that out and making sure that it's solving the real world problems that people have.
I mentioned that there are these three big forks to how we drive accuracy at Myst. We leverage open source machine learning libraries, we bring in the best data, and then we bridge the two with this AutoML engine. So I think what's on the horizon is plugging away at each of those. So on the ML side, making sure we're keeping up with the latest and greatest, having all of the kind of best modeling approaches plugged into the Myst platform. On the data side, we are going to have a big focus this year on expanding our third-party data catalog farther to enable even more accurate and also more domains of targets that we forecast. Something we haven't talked about yet, I think, in this podcast is renewable generation forecasting, but that's another one that benefits from some specific third-party data providers. And then on the AutoML engine side, I think this is one where we'll spend more and more time over time. So I think I mentioned that we offer domain-specific AutoML solutions where in the near term, those domains might include things like load forecasting, forecasting different price signals, renewable generation. But there are a couple ways those expand. So one is expanding to new domains, of course, which will always involve new R&D and new third-party data. And the other is expanding our capabilities within one domain, considering a much larger potential feature set. As our catalog grows, that's going to require continued R&D on the actual optimization side.
Well, I think one of the reasons to be attracted to climate change and energy is because it's so impactful and important, one might even say critical for the world right now. If I'm a trained statistician, I'm not an ecologist, there's not often an obvious path for how to help. For someone who as well has that passion, do you have any advice for how to craft their career to get specifically into energy and companies like what Myst does?
So something I learned when I was doing my survey of climate tech opportunities is there are a number of them, but maybe I'll call out 4 kind of sectors I saw as pretty appealing to those in the ML space in case this helps direct anyone's research. So obviously clean energy is the one that I chose and I'm very excited about. There are also some really cool problems in transportation, big data sets that can help city planners or help reduce emissions. There's increasingly more and more machine learning in agriculture. So, there are methane emissions from agriculture and maybe changes to farming practices and changes to, the application of fertilizer and stuff like that could have non-trivial climate impact. And then kind of under the general header of remote sensing, there's cool stuff too. Things like, kind of automated monitoring of reforestation, monitoring and quantification, and, methane emissions monitoring and mapping. These are all awesome applications of machine learning that I hope continue to grow.
And of course, I would love to plug to just keep an eye out for Myst specifically. You can check us out at blog.myst.ai. And, whether you're a potential future candidate or a customer, we'd love to hear from you. If you want to learn more, you can email us at hello@myst.ai. We expect to be hiring more data scientists and software engineers sometime in 2022.
Erin, thank you so much for coming on Data Skeptic.
Yeah, thank you, Kyle. This has been fun.
That concludes another installment of Data Skeptic Time Series. Our guest today, Erin Boyle. Thanks to our sponsor, Nomad Data, and our annual sponsor, Weights and Biases. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, and our host, Kyle Polich.